This video will be on section 3.5, implicit differentiation. This section isn't going to involve a new derivative rule. It's just a acknowledgement of you can do the derivative in a slightly different way. So if you're comfortable with the chain rule, the product rule, the quotient rule, pretty much all the rules up until this point, really this section has the smallest leap typically between all the previous ones because there's not going to be any new rules like that. Right, but what is implicit differentiation and what is it used for? Pretty much anytime you have an equation where the equation cannot be solved for y, we use implicit differentiation. The reason for that is the picture that the graph makes is not a function, meaning it won't pass the vertical line test. So you should have at least some kind of idea of what I'm talking about. In order for a graph to be a function, it has to pass the vertical line test. Meaning if you draw a vertical line, it only hits the graph once at every vertical line. And hopefully you remember this equation x squared plus y squared equals 1 is a circle. Right? I'm not going to give specific coordinates or anything, but it looks something like this. This is the x and y axis, that's our circle. And then this fails the vertical line test because I can draw a vertical line here and it hits 2 points. Pretty much, we're not going to graph these things, but anytime you have a function that fails or a graph that fails the vertical line test, you cannot solve for y and do the derivative. If you think back to all the other derivatives we've done in this class, we always had y equals or f of x equals or something like that. But if you can't get it in that form, then you have to use implicit differentiation. Right? And another way to know that is if you attempt to solve for y, then when you get this y squared by itself, then when you do the square root, you have to do a plus or minus. So you get two different equations, which is also no good. But I think this explanation is a little bit easier because it's more familiar, the idea of a function. All right, so what we'll do is start by working as an example that could have been solved for y. So really, for this one, we can check our answer and make sure it makes sense. But the idea with implicit differentiation is very straightforward. And it really just means do the derivative of each side of your equation. And I like to think of it even more straightforward as do the derivative of every term on both sides. Okay, right, now because we have two different letters here, you can see in this first one when we do the derivative of every term, we'll have to do the derivative of something with x and something with y. That's really the main new thing, is how do we do that correctly. Okay, so the first, it says find y prime, all right, or dy over dx, because that means the same thing, of this function. And the first one we have here, 5x plus 7y plus 6 equals 0. Sorry, this equation, it's not necessarily a function. So we do implicit differentiation because y is not solved by itself. Do the derivative. What we have to do it is with respect to x because we want y prime. And I'll, this is a detail that may have been brushed over prior because we didn't have a choice here. So I'll just explain why as we go through it. Do the derivative with respect to x of each term on both sides. So do implicit differentiation is really what we're saying. For the exact reason I described above, it's not solved for y. So the derivative with respect to x, the reason for that is the way we write y prime. Y is our dependent variable. Y is not the thing we want to find the derivative with respect to. If this said x prime, then we would actually do d over dy. Since it says y prime, we want to do d over dx of everything. So we do the derivative with respect to x of 5x plus the derivative with respect to x of 7y plus the derivative with respect to x of 6 equals the derivative with respect to x of 0. Now 3 of these terms are pretty much exactly like we did before. Right? This one, and this one we could have done before. The reason is the only, let me actually go ahead and write it first. And we will do this the same as before. Since the thing we want to do the derivative of so here the 5x, the 6, and the 0 are only using the variable. So the variable we want to do the derivative of x or numbers. All right, so all 3 of these we would do exactly the same. The derivative with respect to x of 5x, well, that's just 5. I'm going to leave this one blank for a second. The derivative of a number is just 0. And the derivative of a number, even though it is 0, is also 0. Right, now how do we do the derivative with respect to x of 7y? Recall, this is why we had to learn the chain rule first, is I used kind of the formulas with u when we did the chain rule formulas. So we do the derivative and then we multiply by the derivative of the inside. Although this one looks kind of weird. But what I'll say here is since y is not x, different letter, we must use the chain rule. So the variable inside is not the variable we want to do the derivative with respect to. Do the chain rule. Right. So think about the chain rule. What does the chain rule say? The chain rule says do the derivative as if it was x. The derivative of 7x is just 7. So that's our regular rule part. And then we multiply, since we have to do the chain rule, we multiply by the derivative of the inside. But the inside here is just y. And the derivative of y is exactly that. The derivative of y is the derivative of y. So that's what's really more confusing here. Right, so normally we don't ever write this, but if I wanted to do the chain rule with 5x, I would do the derivative of 5x, which is 5, and then I would multiply by the derivative of the inside, the derivative of x, which is actually just x, or sorry, 1, because that's the letter that matches. The derivative of x is 1. But here, since the derivative of y, it doesn't match our x, it is that. If we had any other letter besides x here, like z or t or f or w or whatever, we would also have d of that letter over dx. Right. So that is the key here. But now what you do, we solve for dy over dx. And I'm going to rewrite the equation that we have. So we have 5 plus 7 times dy over dx equals 0. divide by, or sorry, not divide, subtract 5. This is really just kind of like an x or a y or whatever. It's representing something. So we solve for it by getting it by itself, just like any other letter. We get 7 equals, not forget the dy over dx, 7 times dy over dx equals -5, and then divide each side by 7. And our final answer here, we got dy over dx equals -5 over 7. And that is the answer, right? It doesn't matter if it's asking for y prime or dy over dx because they mean the same thing. So our answer is -5 over 7. Right. Now, what I was saying about at the beginning about solving for y and doing the derivative that way, if you can solve for y, that's still a valid way. I just recommend trying this new way because not all of them you'll be able to solve for y. And I'll let you really do most of that on your own. So this is just the checking part. If you solve for y in your equation here, we subtract the 5x and the 6 over and divide by the 7. Right, so it'll take a couple of steps, but you should be able to get to this. And then the derivative of this, since y is by itself, you do the typical derivative, and the derivative of a number times x is the number, -5 over 7. The derivative of just the number is 0, and you see that it matches. Really what we do when we do the derivative here, we're really doing the derivative of both sides, like implicit differentiation, but because y is by itself, it's just dy over dx. We really don't talk about that detail when y is solved for. But if it's not by itself, then we have to make sure we introduce it on our own. Right, but number 2, it could also be solved for y and then do the derivative that way. I'm not going to do the checking part because I just want to practice this some more. And then we'll get into problems where we couldn't solve for y anyway. All right, so once again, y is not by itself. Do the derivative of both sides, so of everything, on both sides, since y is not solved for. Right, so we do the derivative with respect to x of y minus the derivative with respect to x of 3x cubed plus the derivative with respect to x of 8 equals the derivative with respect to x of 0. Right. And the right side's not always 0, so don't get in the habit of just writing the right side by itself. It does match when it's 0, but you got to make sure you're doing the derivative. So the derivative of y with respect to x, really y is like a 1 times y. The derivative of 1, x, is just 1. And the derivative of the y is just itself. Very often what people see with implicit differentiation is every time you see that off letter, so in this example, the y doesn't match the x, you do the derivative as if it was x, and then you multiply by dy over dx, which is a fine way to think about it. Now the rest of the terms, just like the previous problem, don't involve y, it's just x or numbers, so we can do them like old. The derivative of 3x cubed, do the power rule, we get 9x squared, plus the derivative of 8 is 0, equals the derivative of 0, which is also 0. Okay. Now you've done all the derivatives, solve for dy over dx, just like before. Right, I don't need the 1 here. Multiplying by 1 doesn't do anything, so we got dy over dx minus 9x squared equals 0. All the rest are 0. And all we have to do is add the 9x squared to each side. And that works out pretty easily for us. dy over dx, or y prime, whichever one it wants. They mean the same thing, equals 9x squared. All right, but if you want to solve for y, which you can here because it's just y, and check your answer by doing the derivative, you can. All right, but now let's go ahead and move on to one where we couldn't solve for y. So number 3 here, we want to get dy over dx, and we have 9x cubed minus y squared minus 8 equals 0. Now this one, the reason you can't solve for y is like the example I had at the beginning. Since there's a y squared, if you get the y squared by itself and then do the square root, you get plus or minus. So there's 2 equations. But more importantly, the reason why we want to use implicit differentiation is just because y is not already by itself. So we don't need to do that. So we do implicit differentiation. We do the derivative of everything. Oops. Y squared minus the derivative with respect to x of 8 equals the derivative with respect to x of 0. Right. Now the first one over here on the left involves just x, so it's our ordinary derivative. The derivative of 9x cubed is 27x squared from the power rule. Now I think this is one where it'll help click more what we're doing because we have to do something here. The derivative of y squared, if we had x squared, we know we would do the derivative of that is 2x, so we get 2y, the power rule part. And then all you do from the chain rule is multiply by the derivative of y with respect to x, which is exactly the same as before. I don't really need to write that ending part. Okay, so I think it really makes a lot more sense here when you actually have a power or something to do with it, because you're just doing the derivative with dy over dx multiplied by the ordinary rule. That's all the chain rule tells you, right? All the chain rule tells you is do the derivative normally, and if the thing's not just x, multiply by the derivative of that thing. Here, that thing is y, so that's what we got. Okay, then we got minus the derivative of a number is 0 equals the derivative of a number which is also 0. Once we've done all that, now, just like before, we solve for dy over dx. So we've got 27x squared minus 2y times dy over dx equals 0. Subtract the 27x squared to both sides, getting dy over dx by itself. So we got negative 2y times dy over dx equals negative 27x squared. And we do have to divide by the negative 2y to get the dy over dx by itself. And this time your formula looks kind of weird because it has a y in it. The double negatives cancel on the right, but that is okay. When you do implicit differentiation, especially if you can't solve for y like we can't here, your answer will very often, if not every time, have a y in it. So you get 27x squared over 2y. And that's actually correct. Your formula can have a y in it when you do implicit differentiation. And so that's something to keep in mind. It does look kind of weird at first, but that's okay. Number 4 here. Number 4, we got 8 times x times y plus y minus 68 equals 0. Once again, we're looking at this and we want to do implicit differentiation because y is not by itself. Okay, so I'm just going to start writing do implicit for the same reasons as above. Y is not by itself. That means do the derivative of each part. So we want to do the derivative of 8x times y plus the derivative of y minus the derivative of 68 equals the derivative of 0. Now the first one here, especially because we haven't done one yet, can look a little tricky because we have a multiplication here. We do have to use the product rule because we're multiplying 8x times y. Think about if y was replaced with e to the x, we'd have to use the product rule. Same idea. We have a different letter, we have a different function, we must use the product rule here. So we got to do the derivative of the first, which is the 8x. And then the second part we're viewing as y. Right, and let's go ahead and write down the product rule. Says we do the derivative of the first times the second plus the first times the derivative of the second. Right, that's the whole product rule part. So just to avoid confusion, that came from this. And then we're just bringing the other two down. If you want to do the derivatives of them already, you can. If you want to just wait and do it all at once, that's up to you. Okay, but now that we took care of the product rule, now we can do the individual derivatives. All right, so the first part, the derivative of 8x, that's just our normal 8, and that's multiplied by y, plus the derivative of 8x times the derivative of y. This is one that we dealt with before, it's just itself, dy over dx. Right, because really the derivative of x would be just 1, and then we multiply by dy over dx. Plus the derivative of y with respect to x is the same thing here, dy over dx. Minus the derivative of 68, which is 0, equals the derivative of 0, which is also 0. Right, but at this point we have done all the derivatives. And now we need to solve for dy over dx. All right, so we've got 8y plus 8 times x times dy over dx plus dy over dx equals 0. Now to solve for dy over dx, we have two of them. The goal with something like this is to always get everything without the dy over dx to the other side and then factor it out. So we subtract the 8y from each side. That's the only thing without a dy over dx in it. We got 8x times dy over dx plus dy over dx equals negative 8y. And now factor out the dy over dx. It's just like a different letter, different variable. You can factor it out like any number or variable. Right. Let's go ahead and do that. We got dy over dx taken out. And on the left side, the first term here, we have an 8x left. In the second term, we took out the whole thing, so there's a 1 left. And that equals negative 8y. And now we divide by the 8x plus 1. Get the dy over dx by itself. And our final answer, I'm going to not try to use any more room for the next one. So we got dy over dx equals negative 8y over 8x plus 1. Right? But that's all there is when we have the product rule. Right? So just look out for that. You know, we could have powers here like 8x squared or 8y squared or something like that, and you would just proceed the same way. Right, so the last two are really just examples since we only dealt with like the power rule and the product rule. Make sure if we have an e or a natural log working in one of these problems that we can do it just as well. The number 5 here we have 32 e to the y equals x to the 5th minus y to the 5th. Right, we're going to do the implicit differentiation because y is not by itself. So we're going to do the derivative of each side. We're going to do the derivative of everything. D over dx of 32 e to the y equals d over dx of x to the 5th minus d over dx of y to the 5th. Right, now we do the derivative of each part. Right, on the left side here, it does have a y in it, but since we're doing the derivative of e raised to something, we start by just leaving that alone. So the 32 sticks around. The derivative of e to the y starts with just itself. And then we multiply by the derivative of y, the exponent, which is itself. That's the chain rule part. And that's just a reminder from last section in case still a little shaky on that. Equals the derivative of x to the 5th, since that's just x, that's our normal 5x to the 4th, minus the derivative of y to the 5th. Right? The derivative of y to the 5th, we think about it as x when we start, so we get 5y to the 4th. But then, because it's y and not x, we must multiply by the derivative of the inside, the derivative of y. Right, so same thing. Once again, hopefully you're seeing that pattern repeating. Every time we have a y somewhere, we get a multiplication with dy over dx. Otherwise, it's the same exact thing as if we have x. That's the chain rule. All right, and now we want to solve for dy over dx. So I'm going to write down what we've got. Just to give myself room to work. Since we want to solve for dy over dx, we have the dy over dx's on different side. We want to get them to the same side. So last time we didn't have to do that because they were already on the same side, but now we have to get them to the same side. And then we do the same exact thing as before, factor, divide, whatever happens after that. All right, so we want to get this term, the 5y to the 4th, dy over dx, to the left side. Would be the easiest way to make them on one side. Right, because when we get them to one side, we want everything else on the other, and this will keep it that way. Right. So on the left, we got 32 e to the y times dy over dx plus 5y to the 4th dy over dx equals, on the right side now, is only 5x to the 4th. Right, now we factor dy over dx out. That's the only way to get from multiple of them down to 1. On the inside, we have 32 e to the y plus 5y to the 4th. And then that equals 5x to the 4th. And then we divide each side by the 32 e to the y. plus 5y to the fourth. And then we can knock these things out and we get dy over dx. Our formula is this, 5x to the fourth over 32e to the y plus 5y to the fourth. So we can do it like that. Sometimes the way it works out when you have multiple y's in spots like this, some people like to put everything with a y on one side and everything without y on the other, and then do the derivative. Right, so like add the y to the fifth over here first, which is fine. Really, it's just doing this step, but earlier. And the reason some people like doing that is they know wherever there's a y, I'm going to get a dy over dx, and I'm going to need them on the same side at the end. Right, but that's really the only thing you can do differently from what we've done here. Everything else must follow the same way. Right, so I'm going to do it this way with the last one, and I'm also going to add in one other thing. So what we're going to do is compute dy over dx like we did before, and evaluate at 1, 1. All right, so what this is going to mean is after we get dy over dx, we're going to plug in x equals 1 and y equals 1. So that's to get the slope at that point. And the reason I like to just acknowledge one of these, typically when we get the derivatives from previous sections, we have only x in their formula, so we only have to plug in x. If you see this on the homework and since you haven't been shown it at this point, it might be kind of weird. How do I actually do that? Well, it's giving you an x and y because your formula has an x and y in it. It's necessary. Whereas before we only needed an x value. Right? But once again, we have y not solved for, so we're going to do implicit. What I'm going to do, this is optional, like I mentioned before, but I'm going to get the y's on one side first. Then do the derivatives. Right, it's totally up to you. You can do it like I did the previous one, all the previous ones, or you can do it like this. So I'm going to add the y cubed to the right, so that gives me the y's on one side. And now do the derivatives. Right, but once again, it's up to you. You don't have to do this first. You could have just done the derivative of everything first and then gone with it. Don't need that straight mark. So we're doing the derivative of everything. On the left side, since that's just our x stuff, that's our normal derivative. The derivative of x to the fifth is 5x to the fourth. On the right side, the derivative of y cubed, we do 3y squared, but from the chain rule, we multiply by dy over dx, plus the derivative of the natural log of x. We know that is 1 over x, but we have y, so make sure it's 1 over y. And then you multiply by the derivative of the inside. The derivative of y is exactly itself. Right, but once again, if you kind of think about doing when you do implicit differentiation, everything that doesn't match the letter down here, every term, you do the normal derivative as if it was x, and then you multiply by the dy over dx or dz or whatever letter you may have. And I can't stress that enough because I know that's the main confusion in this section is this dy over dx. All right, but now that we've done the derivative of everything, now we can Since I did it preliminary, I can factor out the dy over dx and solve for it. So the left side is just the 5x to the fourth by itself. The right side, I take out the dy over dx. The first term is left with 3y squared. In the second term, we're left with 1 over y. And some people ask, should I simplify this? You can. You can get a common denominator and make it one fraction. But it's not necessary because all we're doing is going to plug in a pair of numbers afterwards, and that's it. So now I'm just going to divide by the 3y squared plus 1 over y. And we get, I'm going to write the dy over dx on the left side just so I can read it more easily. And dy over dx equals 5x to the fourth on top. And on the bottom, 3y squared plus 1 over y. So that is our derivative. Now the added part is to evaluate it at 1, 1. So remember, that's my extra part here for this problem, just so I show you that. If you want to evaluate at 1, 1, you might see it written like this, dy over dx, and then a vertical bar is the evaluation bar. And right on the bottom here, you'll see the 1, 1. What this is telling you is exactly that. Plug in 1 for x and y, but x comma y. If they're not the same number, of course, do the appropriate numbers. So we get 5 times 1 to the fourth over 3 times 1 squared plus 1 over 1. And then simplify this number. 5 times 1 to the fourth is 5. On the bottom, we have 3 times 1 squared is 3, plus 1 over 1, which is 1, and 3 plus 1 is 4. So the derivative at this point, dy over dx, is 5 over 4. Right. And of course, just like before when we dealt with derivatives, if you plug in a number, you should get out a number. That's exactly what's going on here.